Okay, calculus. We are looking at part 2 of these Riemann sums, where we had the left, the right, the middle, and the trapezoid type areas. So we're going to be seeing which ones are we using here and how does it make sense with the information. This is a much bigger deal as far as how things pertain to the AP test, because this interpretation or this meaning of area, that's where the AP test likes to focus on. So let's take a look at this first one. It says a car comes to a stop 5 seconds after the driver slams on the brakes. That's what's happening here. 1, 2, 3, 4, 5. While the brakes are on, the following velocities are recorded. Estimate the total distance the car took to stop. Well, let's go ahead and plot this information and then kind of go from there. And then we'll talk a little bit about area with velocity and how that pertains to distance. So let's start. Area. We got vertical and horizontal lines. So there's a vertical line. Here's a horizontal line. We're looking at this from 0, 1, 2, 3, 4, 5. So let's split it up here. We got 1, 2, 3, 4, 5. So here's time down here. Time in seconds. And then on top, eventually at 5 we hit 0 feet per second, but this is really velocity, or v of t, I guess you could say. So velocity. We're at 0, and we start 0 seconds at 88. So I don't know, let's make 8 marks and maybe or 9 marks and do it in terms of 10. So we got, this is 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, it's not exactly even, but close enough. And we'll see what's happening with these calculations and how they help us find distance. So at time equals 0 right here at this point, and that's 88 feet per second. And then at time equals 1, we're at 60 feet per second, so about here. And then at time equals 2, we're at 40 feet per second, so we're about here. And 3 seconds, 25 feet, so we're about halfway between these two, so about here. And then 4 seconds, time equals 10. There we go. So it makes almost a triangle, not exactly. We're a little bit off, especially right here with these 3 seconds, because we dropped 15 and then 15, and then this will drop was 20, and here's a drop of 10, and here's a drop of 28. So our movements are not exactly linear. We got a big drop, a couple more big drops, then some smaller drops. And these smaller drops would look even more small if this was an accurate scale over here on the side. So anyways, there's kind of our braking. Now this is velocity. This is measured in feet per second here. Feet per second. But what it's really asking us is distance. So I like to think of the dirt formula. D equals rate times time. Distance equals rate times time. This is more commonly looked at as distance over time equals your rate, how fast you're doing. But D equals RT is going to help us here. So if we take our rate times our time, so in other words our velocity times our time, that's going to give us a distance. So what we're going to do is multiply it. We'll consider this to be like our height. This is our base. And we're really just multiplying rectangles. So let's start out with, I don't know, let's do a left side. A left sum, you could say. That means we'll do this one in red. That means that right here, this first box is going to be outside, just like that. And the next box is going to be here. Then the next box is going to be here. And then here, and then here. So there's our 5 boxes, which is actually going to be an overestimate, because notice that these boxes are all outside the curve. we're counting more area than is actually under this line of data. Okay, so the left sum, we're looking at these boxes. Notice each box is just 1 wide because it's 0 to 1, 1 to 2, 2 to 3, and so on. I'm just going to do this with 6 boxes. So we're always going to take, it's each of these boxes. We got 1, 2, 3, 4, 5 boxes. So we got box 1 plus box 2 plus box 3 plus box 4 plus box 5. And we just need to calculate each individual area, then add them all up. Well, the first box is pretty easy. It's 88 feet tall, or 88 units tall and 1 unit wide here. So that's going to be 88 times 1. Similarly, the second one is going to be the next number, which was 60. So that's 60 times 1, or just 60. The third one is 40 times 1. The fourth one is 25 times 1. And then the last one is 10 times 1. So we just add up all those numbers. And that would give us our left sum. Now, if we were to do the right sum, I'll do this in red, that means that the right corner of this rectangle would be touching. And now we're going to be underneath. And what's really weird is this last one is actually 0 tall, that last box. So now when we do the same thing, box 1 plus box 2 plus box 3 plus box 4 plus box 5, our right sum, the first box now is this height right here, which is 66, or not 66, 60 times a width of 1. So that's just going to be 60. Now we got plus 40, and it follows that same pattern, 25, and then 10. But notice that last box here is completely flat, no height to it, so the area of a flat box with no height is 0. So we got those two numbers there, those two sums, I guess you could say. Let's kind of combine the two here, and let's make trapezoids. To make a trapezoid, this is going to be a lot more calculation here, but remember it's the average of these two heights here, because it's 1/2 times the two bases, which in this case are two heights, and that's going to be, so the first one is 88 plus 60, and then multiply by the height, which in this case is 1. So we're going to take that. That's just the first box. So now we're looking at trapezoids. The next one would be 1/2. Now we're doing 60 plus, what's the next height to find this next trapezoid? That's going to be 60 plus 40. And then times the height, which in this case is 1 again. And then we got 2 more boxes, or 3 more boxes to do, plus 1/2. Then we got 40 plus 25 times 1, so I'm not even going to write that, plus 1/2 times, what else do we have here? This is going to be 25 plus 10 plus, now the last one is 1/2 of 10 plus 0 times the height, or the base part of this is 1 wide again. So then we would add those up. So I'm going to take a moment. We're going to use a calculator here. I'm going to pause the video pretty much and plug the calculations in. But through the magic of video, it's going to appear in 3, 2, 1. Look at that. It's already there. Did you notice? We calculated that. Well, I just used a calculator, add stuff up. But this kind of makes sense. You know, 223 is over, 223 feet, of course, is overestimate. 135 feet is under, and 179 around the middle, probably the most accurate. So we're talking about approximately 180 feet of stopping distance. Excellent. So the key here is using boxes and trapezoids to find that stopping distance is really what we needed to do. Now I could have done midpoint as well, but I just wanted to show those 3. Midpoint would have just taken the middle between these two heights. It's kind of, actually it's like trapezoid. But in order to do a midpoint, it usually makes midpoint kind of requires that you have information about midpoints. So midpoint needs the vertical value for the midpoints. And if you notice, I know that you could kind of guess where this midpoint was right here on each of these lines, but we don't know that that's exactly where it is because we don't have any of that in-between information. The only ones that we have are these given points. So technically, we couldn't really do midpoint. Trapezoid is kind of a modified version of midpoint there. Okay, so that's question one. Let's look at another one here. So you jump out of an airplane. Before your parachute opens, you fall faster and faster. Your acceleration decreases as you fall because of air resistance. So you jump out and you're falling really fast, and you're actually speeding up, but you're not speeding up like as fast as you were. So the table below gives your acceleration after t seconds. Estimate your velocity after 5 seconds. So there's a couple of things to keep in mind in here. Your initial velocity, your VO I guess you could call it, is 0 because you're not falling until you start to fall. But if you're sitting in the plane, your initial velocity should not be anything. Okay, and this is actually pretty accurate. I mean, if you look at this 9.81, and we're talking meters per second, that is the acceleration of gravity. And it's just slowing the acceleration of gravity, which pulls us towards the Earth because wind is here and we're trying to push through the wind, but it's pushing back against us. So I got to do the same exact thing that we did before. So we're just going to make a vertical and horizontal line. We're going to plot these points. So let's go ahead and plot them here. I'll go ahead and make these marks here. We got 1, 2, 3, 4, and 5. Let's try and even those out a little bit. This one, just a little bit. That looks a little better. Okay, and then for the other direction, how far do we need to go? Well, we start out near 10 and we end near 3, so I guess 10 lines would be probably good. So we're going to make these pretty close together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'll go ahead and mark these. You know, this starts out at 10, and then we get down here to 5, and down here. Then this is acceleration, so this is meters per second squared, and on this other one is just time. This is seconds. So the first one, 9.81. So we're about 10, not quite 10, but pretty close to it. Let's color this in with green so we can see that dot a little bit better. The next dot is at about 8.03, so just above 8. Then we got 6.53, so between 6 and 7, about here. 5.38, probably about there. And then 4.41 is probably about there. It's close to a straight line, but not exact. And then 3.61, so probably about here. So again, we're looking for velocity, and velocity in this case would be in meters per second. It says estimate your velocity. Velocity is a measurement of speed and direction, but in this case we're looking at meters per second. So if we were to take acceleration times time, let's see what that would do for us, for our units, just to make sure. So acceleration is meters per second, but to the power of 2. And then time is in seconds, to the power of 1. So we can simplify here. If we multiply those two things together, we're going to get meters per second. So we are going to get velocity. So velocity, this is kind of interesting. Velocity is the same as acceleration times time. So we got to do these calculations. Let's figure out our boxes. So I'm just going to do left sum and right sum. So how do we set this up? left. We got these boxes, so that means the top right corner is going to be each box. So we're going to be outside these lines with a bunch of boxes that look like this. And then for the right sum, we're going to be underneath it. Excellent. So really, here's our heights. Okay, so now we got our picture. The inside boxes in blue with the blue heights are going to be how we calculate the right sum, because those are hitting it with the right corner of the box, where the left ones are hitting it with the left corner. And just to make sure that we know what we're looking at, this curve or line or whatever it is, this function of acceleration looks like it's about that. So the red ones overestimate, the blue ones underestimate. So let's see what we got. The left sum, we're going to have 5 boxes. So we got box 1 plus box 2 plus box 3 plus box 4 plus box 5. So the first box, again, these are at time equals 1, 2, 3, 4, 5. So each of these widths is just 1. So we're really just looking at the heights. And the height of that first one is given in our table. That's 9.81. So it's 9.81 plus the next one is 8.03 plus the next one is 6.53 plus 5.38, and then the last one here, because it's right here at this corner, this height. What's that height? It's at V of, or A of 4 is 4.41. There we go, 4.41. So it's going to be plus 4.41. And now let's look at the right ones. The difference with the right ones is that we're going to be doing, our first one is here. It's actually at V of, or A of 1. So that's our first box is 8.03. Now remember that the area of each box is the height of the function, so in this case A of t, times the width. But the width of each of these boxes is equal to 1. So that's why I'm really just writing the other number, because anything times 1 is itself. Then we got plus 6.53. Next one is plus 5.38. Then we got plus 4.41. And then the last one, because the last one ends here at A of 5, which is 3.61. So again, by the magic of video, you are going to see the answers in 3, 2, 1. Oh, beat you to it. So the answers are 34.16 and 27.96. Remember, red was an overestimate, blue was an underestimate. In this case, the left sum was over and the right sum was under. That seemed to be the same for both this and the previous question. A lot of that's just because the relationship is very similar. Falling, but our rate is lessening. And then the other one, I can't remember what it was. What was it? Oh, it's stopping, but that kind of slowed down as well. So it's a decreasing function, and a lot of that, the fact that it's decreasing and its concavity is somewhat close here. That's why we're looking at this underestimate versus overestimate, because that kind of stuff changes. If we're looking at a graph that goes up like this, then the left sum would be under, whereas the right sum would be over. This is our right, this is our left. So it really depends on what the curve looks like. So let's look at the last one here. It says Cedar Brook Golf Course is constructing a new green. To estimate the area of the green, a caretaker draws parallel lines 10 feet apart, then measures the width of the green along that line. Okay, so in other words, we got this line, or this green. It's going to look, I don't know, like what. But he's drawing these lines across them, like this. And to find the area of this, we need to just simply calculate the length of a rectangle times the width here. Because the area of a box is just the length times the width, or the base times the height. So notice that it's 10 feet apart. So that automatically tells us that our width between each line is 10 feet. So determine how many square feet of grass sod must be purchased to cover the green if the caretaker is lazy and uses midpoint rectangles to calculate the area. That would be helpful if we knew things about midpoints, but I'm going to show you what he actually did there. It's really short for the midpoints. And then we'll look at B, C, and D, which is a lot more work. So if I'm going to do this, it's probably helpful if I just lay it out like the graphs that we have been looking at. I know it's not going to make a whole lot of sense necessarily how a curvy area can be translated into something more simple and geometric, but it'll work. So let's look at what we got. So we're trying to draw, what do we have here? Horizontal lines. So we got a horizontal line and then a vertical line. Might need to make these a little bit bigger, but let's go ahead and see what we got. So for midpoints, we're going to do this completely separate from the other ones. For midpoints, we need to first have our data on the table here. So let's call this line 0. And this will be line 1, line 2, line 3, line 4, line 5, line 6, line 7, line 8. And remember, in between each of these is 10 feet. So if we were to do midpoint, let's plot these real quick. So we start out at 0. Then the highest we're going to go, it looks like, is about 60. So let's make 6 marks in here. 1, 2, 3, 4, 5, 6. So there will be 60. And then we got 30 halfway, and we can figure out the numbers in between there. 28 is the next one, so it's about here. And then 50 is the one after that, so that'll be, so we're looking at 1, 2, how far do we go? All the way out to 8. 3, 4, 5, 6, 7, and it looks like 8 would be about here. So 2 and 50. 2 and 50. 3 and 62, so now we're getting bigger. And then 4 and 60, so that's pretty close to that other one. 5 and 55, so now we drop down just slightly. 6 and 51, again a small tiny drop. 7 and 30, now we're going to drop quite a bit, almost halfway. And then 8 and 3, so really small down here at the end. So these are the widths, or not the widths, but the lengths of each of these rectangles. So for the first one, if I were to do midpoint, that means I need to split this up such that I can have a middle for each box. So the odds are going to represent my middles, while these longer lines are going to represent the lefts and rights. So I got 4 boxes. Box 1 plus box 2 plus box 3 plus box 4. So for box 1, we're just going to go right here to the middle, and this is our box. For box 3, we're going to use the midpoint, which in this case is at 3. Or for box 2, pardon me. And then the third box is at 5. So there's that one. And then the fourth box is at 7. So I need to find the areas of these 4 boxes. Well, this first one, notice that it's 2 units wide now, and it was 28 tall because we went up from here. This is at 28. So it's going to be 2 times 28. For the second one, our height is at 3, so that's at 62, but our width is still 2. Or I shouldn't even say 2, it's 20, because each of these is 10 wide. Ooh, I almost missed that. We need a smaller eraser. There we go. So this is 20 times 28. And then we have 20 times 62. And then 20 times, how tall is this one? How tall are we at 5? At 5, we're at 55. And this last one was 62. And then the next one's going to be 30. So 20 times 55. And then 20 times 30. So for part A, if he's lazy, it means that we're going to have 20 times 28 plus 20 times 62 plus 20 times 50 plus 20 times 30. Okay, not too bad. All right, so now I'm going to do the same kind of work, but we're going to do it for left and right. And we'll do those on the same set of axes here for parts B and C. So we need a pair of axes, just like we were looking at before. So there's a vertical axis, we need a horizontal axis, and we're going to plot these same points. Let's do it pretty quickly here, just to work our way through. I should have copied and pasted it. That would have been smart. So we got 60 all the way, 30 about halfway, and then we got 40 and 50, 10 and 20. We got to go all the way out to 8. So 1, 2, 3, 4, 5, 6, 7, 8. And we start out at 0. And then we go up to 28. So that's about here. And then 50. So all the way up here. And then 62. So just above the 60. Then back down to the 60. And then next we have 55, so that's about midway between 60 and 50, and then 51, a lot closer to 50. And what else do we have? Now we got 7 and 30 there, and then the last one 8 and 3. Very small. So there are the points, and that's the same thing we had before, same type of graph. So let's do left box. So if I'm doing left box, that means that here is my lines. I'm going to start with the top left corner and then make a box going across, like this for each one. Whereas if I were to do the right box, do that in blue, that means I go to the top right corner and draw a line to the left. And it's kind of hard to tell like which one would be an overestimate or an underestimate because we don't know a lot about the information in between. But often the trapezoid rule will balance those kind of things out. So here's my right boxes. And then the red boxes are here. So this is kind of interesting. It's like sometimes the red boxes are more, sometimes the blue boxes are more. And then of course our curve that's kind of going through the middle. Right, so let's write this out. Part B, is it left or right? Left rectangles. So that's the red ones. Looking at the left sum. Well, we're going to have 8 boxes there, so I'm going to have box 1 plus box 2 plus box 3 all the way to 8. And each of these has a common width. Remember that we said each of these widths was 10. So it's going to be 10 times something, and it's the height. And our first height for the red box is actually the initial value, which in this case was 0. Then we're going to have 10 times the height for the next one, which that height was 28. Then we have 10 times, what's the next one after that? 50. And then 10 times the next one for the box 4. Where are we at? We got 1 box, 2, 3, 4, so we're looking at 62 plus 10 times 60 plus 10 times, what's left? 55. We got 2 more, plus 10 times 51 plus 10 times 30. And I know this is kind of like, well, when do I stop? How do I know how far to go? And the big thing is this last box. Notice that this last box, that height right there, should be 30. So I shouldn't finish with the 3, I should finish with the 30. On the opposite side, looking at it from the right sum, you're going to have, we're not going to start with 0, we're going to start with this first one, which is at 28. So this is going to be 10 times 28 plus, and now we follow that same pattern, but we're going to finish right here at 3. So plus 10 times 50 plus 10 times 62 plus 10 times 60 plus 10 times 55 plus 10 times 51 plus 10 times 30. Or 300. Plus 10 times 3. So there's those 8 boxes. We got 1, 2, 3, 4, 5, 6, 7, 8. We just need to add these up. So again, by the magic of video, let's see what our answers are going to be. And 3, 2. So again, by the magic of video 1, here we go, and the answers are 3360 and 3390. There we go. Again, that's just a calculator, guys. No big deal. Plug in your numbers, add them up, see what you get. The big idea is setting it up and interpreting it. So to look at part D, we're going to make a bunch of trapezoids. Now remember, a trapezoid is going to take 2 numbers, average them, and multiply it by that width. So we're going to have 8 boxes again, so 1/2. But this time we're going to add the first 2 numbers and then multiply it by 10, because that's our width. Well, the first 2 numbers are 0 and 28. And I got to repeat this process. And now I'm going to move on to 28 and the one after that. What's the number after that? 28 and 50. And we're going to multiply that by the width, which in this case is 10. So I got to do this 8 times plus, now I got 50 and 62. Plus 1/2 times 62 and 60. I'm going to go ahead and speed this up with the power of video. And these are all the numbers that we should get. Notice that we're just kind of moving along, but a lot of things get duplicated. And that helps a little bit in calculating stuff. So we got 50, 50, 62, 62, and so on and so on and so on. So what do we got? How are we going to get this answer? Well, again, calculator, so I'm going to pause it now that you know what you should be plugging in. And I'm going to plug it in and see what I get. And there we go. It's 3375. So what does that actually mean? That means that this green is going to be 3,375 feet squared. Seems like kind of big. But I don't know, if we're doing 30 feet by 30 feet, just 30 by 30 is going to be 900 already. So, this one's kind of that, I don't know, 50 by 50 almost. It's like 50 feet by 50 feet. That's a pretty big green. Okay, so can we use this in real life? Definitely. Do we need to estimate areas? Yes, because we got to figure out how to calculate stuff that's irregular. This is an irregular shape. And calculus gives us methods of breaking things up so that we can piece them back together. So there's our answers. That's the end of this video. We're going to be going over a lot more of this type of concept, especially in a more AP style format. This is just warming up. Welcome to the studies of area with calculus.